Hello and good morning to today's presentation entitled Threat Hunting by Clustering Big Data. Shortly, I'll be handing over to Tiago Pereira, Technical Leader for Security Research at Cisco Talos. Before we get started, just a couple of reminders for our viewers today. Please use the pulse functions to the right of your viewing pane to ask questions. And if you haven't already, click the theater mode button under your viewing pane to watch in full screen. I'm going to hand over to Tiago now to start his presentation. Over to you, Tiago.
Thank you, Vanessa. Very happy to be here. Thank you for the opportunity to share this presentation. Good morning, everyone. So I'm Tiago Pereira. I work for Cisco Talos in the security research team. So I do mostly threat research. So looking for new threats, see what new things the bad guys are doing these days. I've been working in security for 17 years now, and in several roles. I started pen testing, then did some incident response, malware research, security research. And I worked in multiple engagements in several companies along these years. As hobbies, I have surfing and kite surfing. Not sure if anyone here with these interests, but it's something I really like doing it. And also important to say, especially in this presentation, I'm not a data scientist, so I'm a security researcher. But I do data analysis frequently as part of the job. So I need to process data, and that's a bit where this presentation was born. So this was something I came up with to do some threat hunting. And I found it was an interesting example of how we can use big data tools to reduce the search space of large data sets. So I'm based in Lisbon, Portugal, and you have my Twitter there. If you feel that you need to ping me, please go ahead. So the agenda. This agenda is based on the problem that many companies have, that security event data easily becomes overwhelming. So security systems produce data constantly. They produce always more data, and we tend to collect it because we want to use it to detect if there are unwanted things happening in our network. But after some time, it's just so much data that the security teams have some trouble dealing with it, and we start making compromises. We start storing shorter time periods of data. We start having the ability to process it and to search for it in efficient ways. So the agenda here is talking a bit about threat hunting very shortly, what it is, what we're talking about here. Then talking about clustering security events with Spark, which is a big data tool. And then we'll go through two examples of clusters that we have found using this technique, and that are that show some of the features and some of the capabilities that these techniques have. So threat hunting, what do we mean? Just so that we are all aligned. What I'm talking about here when I'm talking about threat hunting is to look for unknown threats in a network or in some group of systems, and these threats are usually previously unseen, or something that may have gone undetected by our security layers, and it's mostly a human job. So several teams do this on a weekly basis or on a bi-weekly basis, and have somebody go and look for things that are happening that shouldn't. So what we do usually when we're doing threat hunting is we query the data. We will have a tool, a SIEM, or an Elasticsearch, or a Splunk, or some other product that allows us to do some queries on the log data, on the security data that we have. And if we know what we are looking for example, we heard about this new threat, or we read a report about this new threat, and we want to look for it on the network, we have some IOCs, and we can start there. So we can use these atomic IOCs, for example, IP addresses, domains, sample hashes, and we can start looking for it by querying data. And for this, these tools are great. They work perfectly well. Sometimes, though, we're looking for something, and we don't know what we're looking for. So we don't have any IOCs and filters. We just want to look for what's strange. And there, what we can do is use, or what's usually done is we use more generic IOCs. Instead of looking for hashes and domains, we look for types of commands, behaviors, things that we know are usually used by in attacks. For example, if you look at the bottom image on this page, you'll see the delete shadows, the delete shadows function, which is used a lot by ransomware. So Spark is a big data processing tool. It's open source from Apache, and you can use Python or Java to program it. And basically, it uses distributed processing. So you can have a large cluster of servers, and that way you can process a lot of data in parallel. Data analysis in this presentation, clustering, is all about dividing data into groups without any previous knowledge of that data. We don't have to train a system or give or set up any rules. This should be done by itself. And also, very importantly, the technique that we're showing here, that I'm showing here, can be used on any kind of data set for other purposes. So it's generic. This is an example. Hopefully you'll find it interesting, and hopefully it will also spark some ideas on projects or in tools that you can develop. So clustering data sets. The first and most important step in clustering data sets is to prepare the data. And this means selecting what you want to cluster, which probably is the most important aspect, and encoding the data for processing. This because the tools and the algorithms that we use will need to have the data in a specific format. So in this example, this is the kind of data that we will cluster. So these are, if you look at the top image, system IDs on the left and commands that were executed on that system on the right. So this is what we want to cluster. We want to cluster groups of commands that were used in systems into clusters, because we are hunting for threats using system executed commands in this case. To do that, the first thing that we will do is we will split the command lines into words. And if you look at the bottom image, you'll see that you have the system ID on the left and an array of words on the right. And so this is the initial data that we selected to cluster. Encoding the data is an important step, which means in our case, it will have something similar to what's happening on the top table. So we'll have a system, and we will have the set of words that were extracted from the command lines on that system. And what we need to do is transform it in a vector of counts. And that's what's happening below. We transformed the words into columns, and then we have we simply counted the times each word showed up in each system. So we have system one showed common.exe one time, and ping.exe 2 times. So we have this vector of 1, 2, and 0 because PowerShell was called 0 times. So this formats the data into the format that the Spark function that we will use requires it to be formatted. That's the only reason we are doing this at this point. So what we have now is we selected the data. We chose to cluster groups of commands because if we look at the whole list of commands, we will be looking at data that is very voluminous. So it's just too much data for someone to look into. And what we would have to do is we would be running queries into it, looking at one command, seeing what it does, looking at the system. So it's a very, very slow and inefficient process. So what we want to do is finding similar commands or similar groups of systems that groups of systems that run similar commands. This is exactly what we're looking for. So to do, the first step we'll do is dimensionality reduction. This because when you have terabytes of data a day that we want to process, you need to make it processable even in distributed computing. And the next step will be computing similarity. So we will find pairs of similar systems. And finally, we will group this into clusters. So first step, this will use a library. So Spark provides us with a set of libraries for machine learning. And one of these has a function called minhash LSH. So this is a hashing function that aims to maximize collisions instead of avoiding them. If you think of a hash function like MD5, for example, it will try to minimize collisions. It will try to have a different hash for different data. So here, we want to have the same hashes when the data is similar. And what happens is if you have, for example, two arrays of words and they share 50% of the words, if you turn these into min hashes, you will also have 50% of the hashes being common. So here what we do is we call this function and we effectively reduce the number of features or the columns from 10,744 to 10. So this is a huge reduction and makes it a lot more easy to process the data. If you look at the bottom image, what we have now in our data, we don't have any more comments. What we have now is the system ID on the left, and on the right, the array of hashes, 10 hashes to be more precise. So looking for similarity. Looking for similarity is, in this case, simply a matter of seeing the overlap of hashes. So similar items or similar systems will have a large number of shared hashes, and these similar and not similar systems will have a small number of similar items. So what we need to do here is select a threshold to define what we consider similar and not similar. So this is dependent on the data. In our case, you can see it in the top image, that's 0.2. We're saying that we consider it similar if we have 80% of similar items. And this is it. So when you run this, and this is also a function provided by Spark, you will have pairs like you'll see in this table. So system on the left, then it's another system that is similar, and then the distance between those systems. So from this moment on, what we have is something like this. So if you imagine that on the left, each dot is a system, what we effectively did now is connected systems to other systems. And we have still a big confusion of systems that are connected to each other. And one question that may arise is, does this help with threat hunting? Well, somewhat, but not too much. You still have just systems, and you still need to go through commands one by one, And then, of course, you have the advantage of knowing other systems that have similar comments, and you can look at them also to see how to get some more context of what you're looking at. So the next step here is to use a graphing library. Graphing is very powerful. You can think of algorithms such as the ones used by Google to find the most relevant results given a search. And what we have here is we start with the image on the left, the short one, which is just the set of systems that are connected, and the graph function, what it does is it labels all the components that are connected. So it starts with a component, it gives it a label, in this case, their color. So imagine it starts with a component, label, decides it's white, its color is white, and it starts navigating to components that are connected to it and paints them from the same color, white. So you effectively get a lot of colors. But on that moment, you need to move to the right the image. So to do that, what you do is simply group items by color. And on that moment, you will have a set of clusters that you need to research. So these images that you're seeing are images of actual data, of this actual example of data being executed, or it's a small sample so that the image will be more readable, but it's a sample of this data and how it is actually clustered in the end. So if you look at the data, at the clusters, you now see that, okay, that there's a lot less that I need to look at. And you can start by selecting clusters that you find interesting, either by size or by something else that you find interesting and want to filter them by. And there's also another point, which is there are items which were not clustered. And these are also very interesting because these are systems that are, for some reason, different from all the others. So they may also be worth a look. So at this point, we have the clusters. So we are doing some threat research. We split our cases into clusters, and now we'll start looking at them and see what kind of threats we can find. So the first cluster I'd like to show you is a miner that we found being hidden in Exchange servers. So if you remember, recently Microsoft Exchange was subject to a set of vulnerabilities that were identified and for which exploits were available. So at that time, there were multiple different attacks going on by multiple attackers targeting Microsoft Exchange. An interesting thing about this cluster is that it isolated one instance of the attack. So it did not just cluster together all attacks against Exchange servers, it clustered one instance. So this is very useful because if we do a filter or do a search for only clusters that contain a specific comment that we know is part of an Exchange server, or that we know are Exchange servers, we can effectively get an image of the landscape of what different attacks are going on against Exchange servers. So to show you, these were some of the commands. So it's a big list of commands. I chose 3 of them. And if you look at them, they are very different. And you may wonder, well, how did these different commands get clustered together? And they did so because we are not clustering commands, we're actually clustering systems with similar commands. So the systems all had these 3 commands in them. So this is just a result of the analysis that we found that the process of compromise started with W3WP, which is the IIS service, and ended up creating a hidden service with a miner. So it was that was the actual payload with a very specific set of comments that were clustered. So the last one I'd like to show you is another cluster that's TA551. So this is a known attacker that's financial motivated. But what's interesting here is we decided to cluster only new items. So we created two clusters, one very recent, another older, and we removed everything that was in both. So we kept only clusters that were very recent. So what happened is we found a new cluster with several different commands being executed. These are typical of this TA551. And what we observed is that everything was typical, but the final payload was different, making its cluster separate from the others. So what we noticed is that it had the C2 protocol that was known to be from Bazaar Welder. So at this point, we knew that Bazaar Welder was being dropped by TA551, which is a new behavior. So this is a new behavior, and what followed is that 1 hour later, the Bazaar Welder dropped TrickBot on the system. So with this filter, we found a cluster that revealed a new behavior for a known threat, which was also a very interesting case. So to conclude, data can become overwhelming and does become overwhelming on I think even the most mature companies suffer from this, but security detection is based on data. So in fact, we want to have more data and use it more effectively. So data analysis skills are a valuable tool for security teams to have. And I think we will see, we're already seeing it, but we'll see more and more of these skills existing in security teams. So clustering, these examples that I showed you, this is a divide and conquer approach. And it's important that we do this, but it's also important that these techniques and many other techniques of data analysis provide automation opportunities that we should consider in our security processes. So data analysis is today very important for security. And this is what I had to show you today. So thank you very much for your attention, and hope you find it interesting.
Thank you so much, Tiago. That was a really great presentation. Thank you so much, everyone, for joining us. Unfortunately, we don't really have time for the Q&A. We're overrunning a little bit. So there's a question in the polls, Tiago, so I'll direct you to it. Maybe you can answer them there directly. So thank you so much, everyone. Thank you. I'll see you in the next session. Thank you, Tiago. Bye-bye.
Thank you.